I'm ready to start. Good morning. Today we will be presenting about the connection between linear algebra and neural networks, and it will be Josh, Matthew, and myself. Just keep in mind that I am not a CS person; the other two are. So during the last week, especially yesterday, I was hard crash coursing stuff regarding neural networks and all this field. So just coming from physics, I've gone to conferences. They're like, oh, machine learning, oh, neural networks, and hearing my roommate and his brother like, oh, machine learning, neural networks, and I was like, cool. And I always keep hearing, oh yeah, there's a lot of linear algebra, there's a lot of all these kinds of math in it, and so pretty much what I will be presenting on is how I process this information. So this is more for those who have kind of no clue about neural networks, pretty much like me. So if you know a little bit about neural networks, very nice, but that's pretty much where the level of my set is presented by. So, oh, what is? Your computer is weird, Boston.
Go to view and make sure it's a single slide. Just go up, yeah. The top bar, menu, left, up, 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 up.
Wait, where?
Right there.
Oh. I also don't have a Mac.
Down, single page, right there, up, up, there you go.
Ah, okay.
And now full screen. Green button.
Thank you. Oh, nice. Cool. So, as I said before, we keep hearing about these terms being thrown around, these acronyms being thrown around from CS people. And so we kind of ask ourselves, what is AI? What is ML? What is DL? What do these things stand for? And so AI just stands for artificial intelligence. And it's just an attempt to imitate human intellect and behavior coming from a machine. So that's kind of something that's out there. And machine learning is a subset of AI, so there are many fields in artificial intelligence. And what machine learning does is they use statistical algorithms to learn using using data that they get from somewhere. And neural networks are a subset of machine learning. And what's interesting about neural networks is it's an attempt to basically mimic the human brain. So we know that the brain consists of neurons, and there are these connections, and there are these pretty much interactions between different neurons that kind of, as we think about and process a decision and action, these go off in our brains. And then we have deep learning, and what deep learning is it's a subset of neural networks where a computer basically is given data, and the computer teaches itself how to process and how to learn from the data. So there's this idea of supervised and unsupervised learning, and that's, I think with deep learning, we have it under the unsupervised learning category. And so these are interesting ideas that have applications in all these fields, but they also have a foundation in linear algebra. So we begin by talking about a perceptron. So a perceptron is equivalent to a neuron, but for a computer, or one of these computers. And so it is basically an algorithm that does binary classification to determine whether our inputs belong to a certain, to which class they belong to. That's how we can use it. And a perceptron consists of inputs, it consists of weights, it consists of a weighted summation, it consists of some bias, and an activation function and output. So there's a lot. I think what I was familiar with going in were the usual inputs and outputs. And so here in this little diagram that I drew up for you guys, this is kind of like our perceptron. We have our inputs. We have x1, x2, x3, x4, x5, and x6. And what happens is that these are all fed into this little node right here. And what happens at that node is that there is this summation, this weighted summation that happens. And so once we perform this weighted summation, what we are left with is this value, and this value will be evaluated by some function. So let me give you an example. Let's say that I'm talking to people and I'm like, should I buy a car? Yes or no? And kind of like what these inputs can serve is these inputs can serve like different questionnaires. So, will it help me, quote unquote, get better grades? That could be one of the inputs. Will it help me get a better job? Will it help me have a nice social life, right? And so we can put ones and zeros, yes or no. And once we do this weighted summation, we get some kind of number out. And we say, well, arbitrarily, I can say, if that number is bigger than 0, it's going to be a yes, get the car. If the number is not bigger than 0, then it will be, don't buy the car. So these are kind of, there's a little thought process that happens. But what if instead of inputs we have, or instead of these questions, we have just pictures of something? And so each of these may represent some kind of body part. And so what this does is, this perceptron will do a weighted summation and say, well, if it's bigger than 0, it will be a dog, or if it was less than 0, it will be a dog. So these are just arbitrary. That's pretty much something I've learned on the spot. It was something that I did not, I had little experience, but that's something that I've learned throughout the last week. So this is just a very, very, very simple perceptron model, and now we will just expand it a little bit. So here we have a neural network that's a little bit more advanced than the previous one. And what we have are we have 3 inputs this time. I can pick how many inputs we have. But what's interesting is that now this is what it's called a layer or a hidden layer. So a lot of things happen here that you kind of sometimes don't see as much. And here we have our outputs. So this is what I'm familiar with. And here is where we have some action going on. So let's kind of take our what we learned about in the perceptron model, and notice that for the top perceptron, I can just have this weighted summation. So this input goes to this first perceptron, and it will have a certain weight. This second input will go into the top perceptron, and will have a certain weight. And the third will carry its own weight as well. And so when I add them up, as I said, I get some value. Now, here's the interesting thing, though, is that in this model, we have more than one perceptron. So we have 2, 3, we have 4 perceptrons to deal with. And so the way we do it is we just say, oh, well, because we have 4 perceptrons, we just write a general weighted summation model for each of these perceptrons. So J here is just will represent however many perceptrons you have. So this is kind of like how I thought about it. And as I was reading, this is the connection with linear algebra. So we can have this, we can set this up, but it is also, we can just rewrite it as a product of matrices, the weights acting on your vectors, on your inputs, and adding this bias term to it. So if you do this, you will have a 4x1 matrix. So that's pretty much the revolutionary way of doing neural networks with linear algebra. And the funny thing is that I was looking for more, and I'll kind of get into that. But my roommates kept saying, no, it's just that. So, but there's a lot more to this. This is a very, very simplified model. As I said, it's actually naive. It's a naive approach. So under this naive approach, if we look at this model, so I can also have weights going from these to my output receptors. And so that's pretty much kind of like another example of setting up this matrix here. And the computer will, there are computers out there that will calculate these matrices. And here's the interesting part is that I thought that, we have these weights and we get a value out. But remember, we need to remember that there's an activation function. And so that's kind of what I'm going to talk about. So once for each of these, you get a weighted, you get a summation, you get a value for k. And what happens is that this value of k isn't your final output. You need to stick this inside of a function. And what the function will do is that it will actually give you the kind of the numerical value at that perceptron. So that's kind of where I didn't explain that earlier, but that's where I'm cleaning it up now. And so really, how I had k equals all of this, it should be more k prime because I put these inside of a function. And these are my real values of k, and I'll kind of explain that in the next slide. So here are these types of activation functions. The first one is just a binary step function. So if let's say that the value at a perceptron was positive, then I would give it overall a value of 1. And if it was negative, it would receive a value of 0. So this is an interesting way of going about with these perceptrons and neurons. There's another one that was used, and it was the sigmoid function. And basically, you stick the value at each, you stick that kappa inside of, for the x value, and you get some number out. And that number will be useful later on. And same thing here with hyperbolic tangent. And actually the one that is used nowadays or tends to be used a lot is what they call the ReLU, the rectified linear function. So that's if your value is negative, it's 0, but if it's positive, it's just whatever value it is as a positive number. And so this GIF was supposed to show how, as you do these calculated summations, it was an example of processing the number 9. And notice how here we have our inputs, we have a couple hidden layers. And what's happening, here's the interesting part, because I wanted to visualize this thing, and it's not doable. My roommate confirmed that for sure, after me being stubborn. But it's because each of these layers increases in a level of abstraction. So these neural networks, they see something that we don't. That's kind of the interesting part of it, and it's through a lot of this linear algebra that we've shown. So just in constructing a neural network and training in general, you are in charge of, you can put in however many inputs you want, you can put in however many layers, as we saw in the last example, we had more than my example. You can choose what activation function you want to use. And there's this term, that I'll kind of loosely talk about, and it's an epoch, and it's just a loop through the neural network. And I will talk about more what that means right now. So there are other, like I said, this was my naive approach to how a neural network functions. And there are other processes that I did not discuss that have a little more rigor to it. One of these is a loss function. So once we finally calculate your different outputs, we say, because these are probabilities, we say, well, if the number 9 was given and they said, oh, it's 60% chance that it's the number 9 and it's 30% chance that it's the number 2, what a loss function will do is it will somehow take the difference between what it actually is and what we thought it would be. And what that is useful for is because in backpropagation, we take that value and it learns us, it teaches the computer teaches itself how to guess more correctly. So I think there will be another talk about backpropagation next week, so I won't get to it. But notice I'm hand waving a lot of these two topics. So in general, continuing with our training, our little neural network that we had going on, one thing that we could do is we could initialize this. Usually it's initialized randomly, but because it's arbitrary, I just decided to stick it with once. So after it goes through one loop, meaning it goes through each of these neurons, it goes through the loss function, the backpropagation, it's back at the beginning. Our weighted matrix could look a little different and this weighted matrix is just going to be the matrix of inputs going into this perceptron. So we can have one for each of these in general. Or actually, it's just the first layer, my bad. And this weighted matrix will change as the more data we feed it, the more accurate it will be. And yeah, it's interesting. And yeah, one more thing that I kind of picked up is that when we, just doing the SVD, the single value decomposition, is really useful sometimes because we have, let's say we put in a big matrix into this neural network. That's kind of like what the GIF was going to show you how it's done. What happens is there's a lot of data, and so sometimes we can use SVD to decrease the rank or the size of this matrix. There's a theorem, and I think the theorem is the Eckert-Young-Minsky theorem, and so it decreases the rank of a matrix. And you can, it's nice because it helps us be more efficient with our time. I have to be a little careful with that. But yeah, that's pretty much it from what I've picked up about neural networks. And then Matthew will present.
Okay. So with neural networks, we have this other idea of a convolutional neural network. And so as you can see here, which one's the laser pointer? There we go. As you can see here, this could represent an image. Images are just matrices with, if it's color, then it has 3 channels, so red, green, and blue, and they're just layered on top of each other. But this is a simple, like one, like say a grayscale image, but we're using ones and zeros for this example. And so we have this image, and a convolution is basically, we take this filter, this 3 by 3 area, and then we take the dot product and put it in the top left. And then we slide this filter along by 1, take the dot product of that, put it in the next, and so on and so forth for the rest of the picture. And so this would be a filter of size 9 because the filter would be 9 because it creates this 3 by 3, which is 9. The kernel right here is the size of the filter being passed across, and we're taking the stride of 1 because each time it's only moving across by 1, and then down 1 layer, and then 1 across, and then make the full convolution. And so that is one convolution layer, but this is how we use it in a full convolutional neural network. So we have a picture, the input, and we take the filter, slide it across the image, and we make this new image, the new layer. And we do it over and over until we are satisfied, and we'll talk about more later how we choose what layers to use. And then we flatten the layer and put that in this classification layer to say this is not a horse, it's a zebra. And so now we're going to, for applications, everyone chose to do machine learning and use convolution, some form of convolutional neural network for regression or classification. And so we're going to use it for deep Q learning. But what is Q learning? So when we have a certain environment, we have agent, and at a certain point, so for example, Pac-Man. Pac-Man is the agent. At a certain point in time, he's at a certain state. And at that state, he can take certain actions. And normal Q learning is you have a lookup table. It can be represented as a matrix. And we have just the state and action produce a Q value. But deep Q learning allows us to take just the state, pass it through the neural network, and it will give us a list of actions, the better actions that Pac-Man can take in order to produce a better outcome. And we'll have to choose exactly what action to take. And in the example we use, we'll use a greedy algorithm. We'll get to that in a second. And so this is a deep Q network. And so first, just some initialization. We have the environment, so just to check which environment we're using. And so we have 9 discrete actions it can take. So at any point in time, it can go left, right, up, down. This is for Mrs. Pac-Man. And, or eat a dot, eat a ghost, eat one of the power pellets. And so the reason we use Miss Pac-Man instead of normal Pac-Man is because Miss Pac-Man is non-deterministic. Although in this example, we weren't able to fully get the non-determinism. But basically, the only difference between Pac-Man and Mrs. Pac-Man is the ghosts. In Pac-Man, the ghosts will find the path to you. They each have different personalities, but so they have different algorithms to chase you. But in Mrs. Pac-Man, the ghosts have a chance of going towards you, and they have, the chance, a small chance of also, say, turning away so they don't go to you every single time. And so we're just importing the environment display to show the video because we can't actually do the environment without a video in Collab. And so this is an example of just a random Miss Pac-Man untrained example. So pretty bad, doesn't know which way to go, just turns around, dies very quickly, doesn't get very far. And so we got some more imports and installs. Now we have the pre-processing of the game screen. So our input is this game screen, the state you saw above, and it will take that, turn it to grayscale, so for easy pre-processing, and then we get to our actual network. And so, as you see right here, we have the convolutional layers. These are 2D because we're processing a 2D image. And one thing to note is these convolutional layers do use fast Fourier transforms to do these convolutions really quickly, as was discussed previously in a different presentation. And so we have the layers, we flatten it, so that's where we make it really long and flatten like basically a one array. And then we define our greedy function. So the way this works is at each action that this network produces, we have to choose which one is best. And there are many algorithms to do this, but we chose to use a greedy function, which basically chooses the best option at that time. But we also added in a policy that slowly decreases this. It has a decay over time, so it won't always choose the best. This is to get better fit. And so we initialize our just buffer to store things. Then we have this thing called sample memories. In order for it to learn what it has to take, in order for it to store what it needs to take, it has to have this idea of what's happened in the past, what's going to happen next, so it can sample from these memories in order to get a better idea of what to do. So Devin mentioned epochs, but in this we call it the number of episodes, and we also have epochs. Number of episodes is the main loop we're going through, so the main loop of the entire network, and epochs is how many we go through for the actual Q-learning, the deep Q-learning network. Okay, so here we just build the networks and reduce the sum, basically just set up code to make it all work. And now we compute the loss, and optimize the loss and gradient descent. And so loss here, we do mean squared error, which is, I believe, the N2 norm, as we mentioned in a previous lecture. And so gradient descent, as Reese had mentioned, is going to find so after we feed forward through our network, we go and find the last, the error from the loss function, and with that, we calculate the gradient descent. We're trying to get to the best fit for the data. With that, we backpropagate, which will come in a future lecture, and we'll be able to find the best fit. Okay, now we're going to train the model. We trained it multiple times, having many different episode numbers. And basically, we pre-process the game screen and return the Q values of all possible actions we can take. Then we select an action using the greedy policy, and then select a random action using probability, the 1 epsilon. And we select an action that has a max Q value. Then we select action A. We perform this action in a state. Then we move to a new state and receive a reward. The next state, S prime, is the pre-processed image of the next game screen. And we just continue this loop. We store this transition in the replay buffer, and then we sample some random batches of transitions from the replay buffer and calculate the loss. We know the loss is defined as the squared difference between the Q and predicted Q, so the 2 norm. And so then we perform gradient descent with respect to our actual network parameters in order to minimize this loss. We copy the weights of the training network to the actual network, and we repeat this for m steps. And so that's what all this does. And here is it training to 800 episodes, and each episode has like 800 epochs. You can do the math on that. It's a lot. Yeah. So then we plot the history. And so this history is just the reward Miss Pac-Man got through the entire, each of the different games through training. And as you see, it slowly is going up, but at the end it kind of starts going down a little bit. And now we're going to, this is just code to evaluate it to produce the video. And so then, let's see, which one is this? This would be, yeah, this is a really good, or one of the better games. We weren't able to train so far, and we're also only using greedy, so it can't get as far as we would like. So you see here, it goes down to the left, gets stuck at corners, still dies, but it has gotten to 840. So this is an example of like around 0 to 5 episodes or epochs. It goes, it doesn't really know where to go. It dies really quickly, doesn't get a high score. Then we go to roughly 10 to 50. And for this one, it goes, it can actually find a path, but it gets stuck in a corner. So, you know, not so much better. So 50 to 100. We're going. Still stuck. Not very much better. Okay, now this is where we get a little bit of improvement. We have, it can go further. It learns to evade ghosts a little better. It found the side room. But if you notice, like this time, it was able to find 2 different paths going left and right. But sometimes due to the normal way it works, it goes the same way each time. 800 epochs, roughly. Actually, surprisingly, this was the best score it got, but you'll see why in a second. It goes pretty good first run. Second run. And the third run, where it gets really lucky. It goes, eats that ghost, that's pretty good. But then it gets lucky here and eats 2 more ghosts, getting the high score of 3520, and the cherries appeared. So then we trained one for around 8+ hours. And this is the result. It didn't quite go as well as planned because we are using greedy with a decay over time. So it started slowly getting worse. but it still was able to learn new things, such as it was taking its different paths, avoiding ghosts pretty well. And we have one more example of this right here. So it goes, does a nice dodge, but then gets caught since ghosts are faster. And then it just dies really quick. And so I adapted this notebook from Adrian. Yep.
All right, so we have the typical computer science example of neural nets. Because they are universal approximators and can essentially represent any function, you have your typical computer science solution of, oh, it doesn't work, let's just throw a neural net at it and hopefully it does the job. So time for a pop quiz. Just kidding, it's a quick review that highlights a few key problems from our original basic understanding of a neural network. So first, we'll take another look at the matrix representation of a network. It is a little bit tough to tell from here, but you can tell that you have your input, your weights, your activation, and down below, you can see they're represented as matrices, where you have your weight matrix dotted with your input vector, which will give you your activation functions. A couple key things to note is that your weight matrix and input vector are per layer. So for every layer you have in your network, you'll have another weight times input vector. In your weight matrix, each column corresponds to all the weights that's connected to a single input node, and each row corresponds to the weights that come out of and connect to a single output node. Our input vector can be almost anything, for example, the pixels of an image. And finally, our activation output, which is found at the end of the network, is essentially a vector of the probability of each option as your correct answer. So our basic learning process starts with our input. You'll recognize the dot product here of our weights and our vector, and this essentially represents similarity. You can think feature mapping. So how close is this cat that I put into the model to our representation of what we think a cat is? So you'll have neurons in a layer say at some point, hey, this is what adds up to be a cat. And the dot product shows, does our input somewhere there, is it close to what we think a cat is? Then we have loss and backprop. Loss is essentially how close is our guess to the correct answer. This is what helps train. And then backprop, which come next week to find out how this works in detail, but is essentially learning how to guess more accurately. We're taking our loss, we're feeding it back into the network, and we're saying, okay, this is the direction you should go to get more accurate guesses. So with this in mind, we can assume that there's so many different network parameters to set. Number of layers, nodes, connections, activation functions, even more. Therefore, our model's configuration greatly translates to its accuracy. And so the accuracy of a network is essentially limited by the shape of your model. So here's the problem. This is your machine learning system? Yep, you just pour the data into this big pile of linear algebra, then collect the answers on the other side. Well, what if the answers are wrong? Well, just stir the pile until they start looking right. Unfortunately, this paradigm is all too true in us making neural networks as of current. But what are we supposed to do if our network is wrong or doesn't work as well as we hoped? How do we change it so it works better? Imagine that, it takes 42 neurons, random number, to represent a cat. But the way we've set it up, one of our layers can't fit a cat. Like, there's no indication that any given network configuration guarantees us a most accurate network. So, as was in the comic, our current neural net recipe. You have a company, you have some money, hundreds of thousands of dollars, you're machine learning experts with years of study, and it all comes down to guess and check, their intuition. Let's do this number of nodes, this number of layers, throw together, see if it works. Oh well, you still paid me. I'll just keep guessing until I get one that's okay. So, as any computer science would say, instead of doing the work, let's automate the process. So, there are 3 steps on how to discover a better shape. This is called neural architecture search. Essentially, it's machine learning to make machine learning. Our first step is the search space. So, there are various ways to represent a search space, as depicted by the picture here. We have, you can recall that the matrix representations of these neural networks exist. However, it goes far to help and visualize them as graphs. Theoretically, there are an infinite number of shapes and configurations to do, but we need to limit to a reasonable set of shapes so we can process in a good amount of time and efficiently. Here you'll see we have our standard one that's just a chain. We have a multi-branch one where you can connect many nodes all around. Then we have cells, which is like a multi-branch, but you can use them and build up larger networks out of these cells and kind of hierarchically stack them into even greater networks. Our second step is our optimization strategy. There are, given a shape, how could it be better? So there are 2 main approaches. There are your discrete approaches and one-shot approaches. Your discrete approaches are essentially, I have a circle, let me try a triangle next, then a square. It's very discrete. However, one-shot approaches have been gaining popularity as they are able to continuously represent a network and figure out what's best along that range. Here in the image, we have an example of one-shot emergence. So you have a neural network, you have connections, you don't know what those connections are. You don't know what's best for those connections, so you assign all of the connections, all the colors. And as you train the network, as similarly to if you were training for a sport, you use certain muscles. And as you progress in the sport, certain muscles become stronger because those are the ones you use more. Similarly, we have functions that stand out and are used more. These are then chosen at the end as your dominant muscles and build your final model of the network. Our third step is performance prediction. Because fully training a model takes a lot of time. Even the single model that we did for the Pac-Man example took 8+ hours, and that's just one model. Here we're running through hundreds and hundreds of thousands of models, so it's inefficient to try to fully train every model every step. So we predict accuracy. Then we return that score to our optimizer, which advances exploration. Are you headed in a good direction? Cool, keep going. If you're not, maybe turn left a little, try looking in there. There are 4 basic time-saving methods. We have lower fidelity estimates, which means basically using less data on our model to see how that works. Second, we have our learning curve extrapolation. This is essentially cutting off your slower learners. Say in a class, I don't suggest, but every week you cut off the last 3-4 people who, I don't know, haven't turned in homework or something. Third, you use network morphisms. These are slight changes to the graphs. You add one node, you add one layer, maybe you take one away. Essentially, it's sticking to something close that you have done and just editing it slightly. Finally, you have weight sharing, which is passing on basic knowledge or features like this one already knows what an ear is, so we'll use it over here as well because we've already trained that bit. So here's an example. We'll take it back to adjacency matrices, and you'll note that even though these are random graphs, they are semi-resemblant of neural networks. We have 3 types. We have our undirected, our directed, and our weighted. And you can see our adjacency matrices down below. A couple things to note. First, changing the shape is essentially changing our matrix representation. A adjacency matrix will be a square matrix where n is the number of nodes. Our undirected graphs are symmetric. Our directed graphs are triangular, as you can see from the example here. Then our weighted graphs are could be a mix of either, depending on how you want to represent it. However, they are useful when talking about one-shot emergence. You can think of your weighted graph for one-shot emergence as a graph where there's the third dimension of the multiple ones. So you have multiple layers of weighted graphs where each graph corresponds to a type of layer. As you train the network and build up strengths, the weights of each type of connection in each layer gets stronger. This corresponds to the probability of the connection being the chosen one at the end. And at the end, you can collapse that to your 2D matrix as a weighted matrix. And that is your strongest connections, your final model for what you want to test. So for this experiment, to put it into practice, we want to generate optimized networks, in this case for simple image recognition. Our output networks are convolutional neural networks, as we previously talked about, over CIFAR-10, which is basic images. I use Noslib, which is a modular library. 4 steps is first choose module algorithm for each step. Each of the steps has hundreds of thousands of different implementations. We picked some of the more popular ones, and even though there are 3,000, we tested about 9 of them. Second, we search for the architectures. Every search produces 100 models at 175 epochs each, which is why we can't fully train all of them. But once we find our best model, we throw it into step 3, which is training the best architecture. We train this for 600 models long and 520 epochs. Each of these models represents the next step in learning. So we've trained it a little bit, it's learned so much, we'll save that as a model, train it a little bit more. Finally, we test the model on CIFAR-10 to see how well it does and return our final score. Some examples of models that it can return. This is the first one, where we have a single line, it's simple cell on the right. You'll notice that we have normal and reduction cells that build your macro graph on the right, and you'll notice that there are repetitions. As with most learning applications, repetitions helps learning. Similarly with neural nets. You can see there are different types of connections, overall fairly simple, builds up to a network. Our second model is a little bit more convoluted, where there are 6 different motifs, one which wasn't even used. And these ones all build up to build a larger model. More searches, more time, slightly better accuracy in this case. Another model, you'll notice references the first one that we had, where instead of a single line, even though we have our 2 cells, it is more of a twisted, like DNA looking structure. You will still notice that there are repetitions. We have several normal cells and a reduction cell, several normal cells and a reduction cell, in the exact same amount as well, repeated over and over. This helps our network learn. So if we take a look at the results that we get, we can see that overall the models did fairly well. We're looking at 97, 98, 99% top 5 accuracy on CIFAR-10, which is right around the ballpark of current state-of-the-art methods for hand-picked models. And these are models that experts have worked countless hours on. And this is something that, even though it took, 20, 30 hours to run everything, I set it, let it sit, didn't tweak anything, and it's working about the same. So what can we do with this? Where does this go? Well, neural architecture search is quickly taking over the field of machine learning. You can kind of set it, let it, and forget about it, and when it spits out your model, you're good to go. And even with this detached style, it is setting state-of-the-art results across all of its many applications. Specifically, efficient methods are underexplored, as a lot of this research is restricted to big companies like Google or Facebook, who have supercomputers in their back pockets. Speaking of Facebook, one-shot methods have been proven to be very successful recently, specifically few-shot, which is a tweak that Facebook did on one-shot method a couple months ago and absolutely demolished, like state-of-the-art across the board. Current projects in the field that are going on, interesting applications that other people have been working on. We can generate crazy photos from a description. We can do real-time fluid or material physics simulation. We can model a 3D environment from a photo. There are real-time deepfakes. We can recreate entire video games from scratch, like Pac-Man, not just the AIs. And of course, neural architecture search. And as an example of something that has been generated, the input phrase was teddy bears working on a new AI research on the moon in the 1980s. And this was the image that was generated, completely from scratch.